Alright, so let's talk about rate laws. This right here is the rate law. And what the rate law does is it relates initial concentration and the rate of the reaction. So rate is going to be in molarity per second. It's the change in concentration over time. K is something called the rate constant. And A, of course, is the concentration, initial concentration of a reactant, generic, remember. And then N is the reaction order, and that is A raised to the nth power there. So if N equals 0, that's considered a zero order reaction. And what that means is the rate is independent of the concentration of A, because if A is raised to the 0 power, that means it's just 1. So the rate would be equal to the rate constant. If it's first order, that means the rate's directly proportional to the concentration of A, because the concentration would be raised to the first power. And then if you have second order, then it's proportional to the square of the concentration of A. So let's look at this. A zero order reaction, remember A raised to anything raised to the 0 is 1. So the rate is just equal to K. Now this is the bad part about the rate law. The rate constant units change with each order. So if you look here, we have molarity per second is the rate, and if that has to stand, okay? It's always going to be molarity per second. So if that's equal to K, well, that means that the units of K in a zero order reaction must also be molarity per second. So on a zero order reaction, the units of the rate constant are molarity per second. Now, in a zero order reaction, the concentration of A will decrease linearly with time because the rate of the reaction isn't changing. It's going constant at a constant rate because it is the rate constant. On a first order reaction, you have rate is equal to the rate constant times a molarity, because this is raised to the first power here. So rate has to be molarity per second. Well, we're looking for some units when multiplied by molarity that will give us molarity per second. And so that is 1 over seconds, which that means that it's the same thing. If K is equal to 1 over seconds, that's the same thing as inverse seconds. And a lot of times you'll see it written like this. So in first order, the rate slows down as the reaction proceeds because you're getting less and less reactant concentration. And here on a first order reaction, if you want a linear slope, you have to take the natural log of the concentration of A and graph that versus time. We'll talk about all this again later. Then for second order, the rate, of course, must be molarity per second again. Then we're getting something times molarity, because it's molarity squared here. Well, what would give us these units? Well, we still have to have the seconds on the bottom, right? But now we have to get rid of one of these molarities, so to do that you put a molarity on the bottom also. So for second order, K is going to be equal to 1 over molarity times seconds, which is the same thing as inverse molarity, inverse seconds. And this is how you're going to see it written a lot of times. So I think that is probably a good place to stop. Oh, I forgot to talk about this. To get a linear slope for second order, you have to graph 1 over the concentration of A and graph that versus time. This right here, these are graphs of rate versus concentration depending on the order. So zero order reactions, the rate doesn't change. With first order, as you increase the concentration, the rate also increases, but it's a 1-to-1 ratio. With second order, if you double the concentration, then you quadruple the rate. So you can only find the order of a reaction by experiment. You have to do it, and we look at these and we use the method of initial rates, and I think I'm going to do that on the next video.